going to start on, actually we're going to start and finish, linear, quadratic, and exponential regressions. And I'm going to let you watch a video, actually a Khan Academy video, about how to use a table, which is, if you turn in your packet, it's almost, let's see, the next last page in that packet has the tables on this left side here. He's not going to talk about these specific tables, but he'll talk about something similar to that. So that next to last page is where we're starting. So we're going to go over this as soon as you get through watching the video. If you want to get out the notes and take notes on what he's going to talk about, I think it's about 7 or 8 minutes on the video. So go ahead and find this page, next to last page. Not the last page, next to last page. Alright, so you're going to need, if you want any notes in your actual notebook, you have that ready here. So we're talking about linear, quadratic, and exponentials. And remember, linear just means it is a straight line, no matter what it is. Quadratic, what does it look like? Looks like a U, right? Looks like a U. And exponential looks like a what? It either goes up really quick or goes down really quick, so it looks something like that. And that point is usually 0, 1. So you're going to be getting, there's 2 types of ways you're going to have to identify these things. One of them, they're going to give you a table, and you can look at the table without graphing it. And the table is probably the one they're going to give you on your non-calculator quiz. You're given a table, and they're going to say, is this a linear, a quadratic, or a regression model? And probably the last choice is saying none of the above or something. Probably going to be on the non-calculator quiz. And he's going to show you, and then we'll go over this page here about how to exactly do it. Really simple process. And then we're going to go in using the calculator, given a set of data, and come up with a regression equation, like we've done it with the linear one. So let me get to that video. What video I want. I thought I added it on here already. Maybe I didn't. Alright, so let me go back and find it.
Data sets here, and we need to figure out which of these data sets come from either a linear, quadratic, or exponential function. And just as a reminder, a linear function is of the form y is equal to mx plus b. A quadratic is of the form y is equal to ax squared plus bx plus c, and an exponential is of the form y is equal to some constant, let's call it a, times some number to the x power. Now,
Alright, I'm going to lay that up there so you can, if you want to copy these tables down real quick, and then I'll start it back. That way they're not trying to rush and you can actually listen to what he's saying. You want to leave room out from these tables because he's going to write in between these tables. You can either write them like this, if you're going to need room out front, or you could write them one on top of the other. So leave room beside the tables. You're going to be writing beside those tables.
The way to tell them apart, and I'm going to actually show you, it'll probably be intuitive for you for a linear function, and maybe even for an exponential. The quadratic, the technique I'm going to use might not be intuitive, and I'll actually prove it to you in the next video, or at least show you an example in the general case of why it makes sense. But the way to tell a linear function is that when you increment x by a constant amount, y will always change by a constant amount. So when you always increase x by 1, y should always increase by a certain amount. So let's just using that as our kind of our first guideline, let's see which of these represent a linear function. So over here, so in all of these examples, as we go from one data point to the next, we're increasing x by 1. It's very important that you pay attention to that, because if you weren't, you'd have to adjust things a little bit. But in all of these, we're always increasing x by 1. So let's look at our change in y's. When we go from the first data point to the second data point, our change in y is 60. When we go to the second to the third, our change in y is 90. So that immediately tells us we're not dealing with a linear function. When our change in x is 1, our change in y here is 60, then it's 90, and then as you go here, what is it, it's like 135. So this one is clearly not linear. Let's look at this one over here. Our first change in y is 2. Then our next change in y is 0. Once again, not linear. As we increment x by a constant amount, our y does not increase or decrease at a constant amount. So once again, this one is not linear. Now let's look over here. Once again, we're increasing x by 1 on every data point. And when we go from this first data point to the second data point, y decreases by 3. Then we go from the second to the third, once again, y decreases by 3. Third to the fourth, y decreases by 3. 1 to -2, once again, decreases by.
When he's talking about decreasing, do you understand where he's getting these numbers? He's taking the bottom number and subtracting. So he's saying 180 minus 120, 270 minus 180, 6 minus 4, 6 minus 6, 7 minus 10, 4 minus 7. Does everybody see where those numbers are coming from?
3, and we just keep decreasing by 3. So whenever we change x by 1, when we increase x by 1, y goes down by -3. So we actually have a constant slope. We could say our change in y over change in x is equal to, when goes up by 1, y goes down by 3. This is the definition of slope. This is the m in this equation right here. Our changes are constant. So this one right here is linear. This one right here is linear. Now quadratic, there's an interesting, we could call it a trick right now because I haven't really showed you why it works. But in a quadratic, your changes in y, the changes in y are not going to be constant, as was the case with linear, but the change in the changes of y will be constant. Let me write that down. It probably makes no sense to you right now, but when you see an example, it'll be kind of fun. Change in y constant.
I'll tell you what he's exactly meaning right here. They call this first row, and you'll hear me say this in a minute when the video's over. The first time they subtract is called the first difference. Because it's the first time you're subtracting them, which is different, right? So this is the first difference, 2 zeros. The first difference, all of them are the same. So when this to me is a little confusing, the change and the change. So he's talking about the second difference. So what he's going to start doing is subtracting. Here's the first difference. Now he's going to start subtracting the second column. So the thing about it is subtracting twice. More mathematically, the change in change. Remember, I've alluded to that delta y over delta x, especially when we were talking about slope. That's the change in y over the change in x. Change in just means subtract. And so I want you to get bogged down in his vocabulary.
Constant. Let me show you what I mean. So over here, let's look at this first one over here. So we went from 120 to 180, that was an increase of 60. 180 to 270, that was an increase of 90. And we went from 270 to 405, which is an increase of 135. Now when I talk about the change in the change of y, these are the change in y's. What are the change in the change of y's? Well, we had a change of 60, then we had a change of 90. So that was a change in the change of y of 30, or a difference of the difference. You could do it that way if you like. And we go from, then we had a change of 90, and then we had a change of 135. So the change in the change, let's see, that is 45. So here the change in the change in y, or the difference of the difference, is not constant. We grew by 60, and then we grew by 90, which was 30 more than 60. Then we grew by 135, which is 45 more than 90. So this is not constant over here. So this tells us that this is not a quadratic function. Now let's look at this over here. The change in y, let's write that down. This clearly was not linear. We increased by 2 here, increased by 0 here, increased by -2 here, increased by -4 here, increased by -6 there. The change in y's are definitely not constant, but let's look at the change in the change of y's. So we increased by 2, then we increased by 0. So this was a -2 in the change of y, or the difference of the difference. Then when you go from 0 to -2, we changed by 0, then we changed by -2. That is a change in the change of -2. Then you go from -2 to -4, a change in the change of -2. This was starting to look quadratic. We changed by -4, then we changed by -6. Once again, a change in the change of -2. So this data right here fits our requirement for a quadratic. And I'm just kind of giving it to you as a trick right now. In the next video, I'll actually show you why this works. I'll show you the example, just so you get the gut feeling of why it should work. So this one right here is quadratic. So you might say, hey, Sal's giving us 3 examples. One of them is going to be linear, one of them is going to be quadratic, one is going to be exponential. This one's probably going to be exponential, and you are probably right. But let me give you the way that we can figure out if something is exponential. So when x increases by 1 in an exponential, you should always have a constant multiplying factor. So when you go from one term to the next term, they should be a similar ratio from one to the next. So instead of just subtracting, in this case, 120 from 180 and 180 from 270, to test for an exponential function, what you want to do is check whether the ratio of, when you increment x by a constant amount, whether the ratio of the y's are the same. So when we increased x by 1, y went from 120 to 180. So it increased by 18 over 12 is 1.5. So we went from this term to this term. Let me clear all of this stuff out here. Let me clear this. So when we went from here to here, this was times 1.5. And then when we go from 180 to 270, once again, that looks like we're going times 1.5, right? Half of 180 is 90. Add that to 270. So once again, we're increasing by 1.5. 270 to 405, half of 270 is 135. That's how much we're increasing by. So once again, we're increasing by 1.5. So every step of this way, we are multiplying the previous term by 1.5 to get the next. And that actually tells us that this right here is a 1.5. But our point here isn't to actually figure out the formulas. The point here is to classify them. So now we know definitively that this right here, at least given the data we have, is an exponential function. Anyway, hopefully you found that fun.
Fun? Y'all find that fun? Nobody found it fun?
In the last video, I told you that.
Okay, so here is. All right, here's what he's talking about. On your, now we're looking at the packet. We're looking at the packet now. So if you look at, you're going to be given a table and a graph. Let me just write these numbers down. What? Yeah. Do what? Oh, to get out of the locker. Okay. Alright, so three different types. You've got, or three different representations. You've got a table. This is probably one, like I said, you're going to get when you have a non-calculated portion. They're going to expect you to identify it based on the table, and then they're going to ask you, sometimes they might give you an equation and say, alright, which one is the graph of it, or they might give you the graph and say, come up with the equation. This is going to come up more in the regressions on the equation that we're going to do. The tables, which is what that video talked about a little, it just talks about using the tables. And there are common things that we're going to say the first difference, meaning you subtract one time. Let's see. The second difference, we'll get to that. So what's on your paper that you have there, and he was talking about subtracting -5 minus -7. You'll have, well, you should be able to do that one on your own. -5 minus -7 is going to be 2, and -3 minus -5 is 2. And then if you see so on and so forth, every time you subtract those, it's going to be 2. Now, they're assuming that up here, the difference is always what? 1. Okay? You do have to be careful there. So as long as that difference is always 1, you're okay. So always be sure and check that first. So if you're given a table, go through and subtract the y values. And if all of these numbers are the same or a constant, what they're going to say, if they're a constant, the same constant, doesn't matter what it is, as long as they're all the same number, it's a linear model. Okay? For the quadratic, here's how I remember it. What's the exponent on that x right there? What's the exponent? It's a 1. What's the exponent on this one? A 2. Second difference. So in this one, they subtracted 4 minus 9. Yeah. 1 minus, y'all check my subtraction here. 4 minus 9, 1 minus 4, 0 minus 1, 1 minus 0, 4 minus 1, and 9 minus 4. So I've got a -5, -3, -1, 1, 3, 5. Now think about this. These numbers, what's happening to them? They're starting low and they're getting higher, and they're also symmetrical, aren't they? And it just so happens in this one that it kind of looks, or it is symmetrical. So we know based on that first difference that it isn't a linear model. So if we do it again on all of these, so the first difference and then the second difference, -3, actually it's the same numbers up here, -3 minus -5, -1 minus -3, 1 minus -1, 3 minus 1, and 5 minus 3. So that second difference is constant. So when the second difference is constant, you know it is a quadratic. Now, the exponential is a little bit different. It's not based on the first difference, not based on the second difference, but you do look at the differences and see if they're going up really quick, if they're increasing at a fast rate, or if they're decreasing at a fast rate. And if you go through and subtract these numbers, something happens. And what do you notice on these differences? What do you notice on those green numbers compared to the blue numbers? There's 1/4 in here, 1/2, 1, 2, 4. Yeah, they do, which is kind of a hint. Hey, you're probably looking at an exponential. Do they start really small and increase really fast? Yeah, or it could start small and decrease really fast. It depends on which one it is. So if you have this constant going on here, then you know it's an exponential, which I've got listed over there. And then of course the graphs, you know what the graphs look like. So turn over to the next page, and there's some sample papers. We're going to do some of them. So let's see, let's do, I have no idea what these are. So let's do, right there at your table, or underneath there, I want you to try number, let's try 1, 2, 5, and 15. 1, 2, 5, and 15. And I'm going to write them up here while you're working on them. So 1, 2, 5, and 15. You can put them right there in your notes. You do the differences right there on the worksheet, whichever one you do. But I want you to do those, and after I get them written down, I'll walk around. Yourself. Once you get those in there, check with your neighbors, see what they got. And there is a neither. It could be a neither. So it's either linear, quadratic, exponential, or neither. Let's see, where's my... Okay, so let's come to number 1. All right, ready? Come on up. So just show us those differences. We may need to go further, I don't know. I'll already do this one, check, or finish if you need to. Since it's gives the same thing he does. Don't assume, because the first couple are the same number, that you can stop right there. Always check them all. The ones that you do, we just write the name, whichever one you think it is. All right, so Reed's got all the constant differences is -4, and he's decided it's a linear. You agree or disagree? Pretty easy. All right, you're good. You're off to the number 2 is on split. All right, Hannah. Reed, you just need some candy. I'll bring it back up to you. I got some new fun dips. There's strawberry chocolate strawberry, wonderful watermelon. Good. We agree with Hannah? Exponential? All right, easy enough. All right, 5. Little 5. You want to try? Alexis, come on up. Now, are these not easy problems? You gotta remember how to do them though. You will probably have usually 2 to 3 like this on your ERC, and easy 2 or 3 questions for you to get. So these are like great training answers. These are the ones that you should be able to get no matter what. Well, that was simple enough. Do we agree with that one? All right, these are the candy lessons. What's the last one? Trevor, you got your hand raised or are you stretching? I'm feeling the hand raised. All right, come on. And I'll be quite honest with you, I just learned this trick last summer. This is not the way I had ever done it before, except for, let's see, the first time I ever, actually, they didn't even do regressions when I was in school. They didn't have a name. Never got neither. What do you think? Do we agree? We agree. All right, now look what happened. See, notice these were all negative ones, and then what happened at the end? Positive ones. That's what I said. Don't assume. Does everybody know what happens when you assume? Huh? And y'all not seen this? I don't want to offend anybody, but when you assume, you make a but out of you and me. Don't assume. Okay? Never assume things when you get in trouble. Alright, so that's why I said perfect one right here. How many of you would have stopped right here when you got like 3 negative ones? Be honest. 1 person, 2 people? Well, y'all are the honest ones for now. Okay, so if I assigned all those other ones there, anybody could do them? Or anybody couldn't do them? We're good? Alright, now, let's move more to where we're using the calculator when we're doing the regressions. So, get your calculators out, and we're going to be, there are 3 types of regressions that you're going to be responsible for on the test. And we've actually gone over all 3 types, linear, quadratic, and exponential, but we haven't actually run the regressions on all 3 of them. So, on your regressions, let's clear everything out. So make sure you don't have anything in y equals. You want to make sure your home screen's clear, all that good kind of stuff. Okay? You may remember where the regression is. We did it the other day, actually. When we were putting numbers in the calculator, we were putting them in the list. And then what did we do? Stat, calc, 4. So go to the stat button right now. I want to make sure everybody knows where we're going. We're calculating regressions is what we're doing. So, well, let me write this in. So the first thing you're going to do is you're going to input your table or your points, however they give them to you. Input your table or your points. And so you're going to go to stat. Edit. Number 1, there we go, number 1, and then you're going to put your X's in L1 and your Y's in L2. Well, there's the one thing that is very important that you do not do here. In our list, what's the one important thing that you never, ever, ever, ever do? Hit delete. Do not hit delete. Because what's going to happen, don't delete. Do not use that delete button. Because these regressions are run off L1 and L2 automatically. If you delete L1 and L2, you're not going to be able to put, I can show you how, but I just don't know if you'll remember it. Alright, so you're going to put them in the table. Second thing, you're going to choose the regression. And you might have to do all 3. You don't know. So you're going to choose the regression. So on that calculator, when we go to stack calc, the ones you're going to be working with are number 4, the linear regression, number 5, the quadratic regression, and 0, the exponential regression. So 4, 5, and 0. So back over here, you're going to choose a regression. So you're going to go to stat, calc, and then from there you're going to either choose a 4, which is the linear regression, 5, which is the quadratic regression, or 0, which is the exponential regression. Now, can anybody remember once we run this regression, the calculator does all these numbers. Anybody remember the one thing that's very important that we're going to be looking at? The one that tells us whether it's a good fit or not. But this is also called a line of best fit. Very, very important. You've got to make sure it's turned on your calculator. Anybody remember what tells us makes it a good fit? No. One thing in that calculator. Well, let's just do one. Let's just put in this first one where it says I'm on the next page, or the right beside where those tables were that you just did. Let's put in those first points there. Very important you know where this button is in case your calculator will be reset, so you automatically have to know where to go. Alright, so we're going to stat, edit. I got to clear my L1, so remember, what do? So highlight L1, hit clear, and enter. Do not hit delete. Do not hit delete. Alright, so let's put them in 20, 30, 40, 50. Just looking at those, what do you think this is going to be? Linear, quadratic, or exponential? Take a guess. The x's are going up by what? 10. Do the y's look like they're increasing or decreasing a whole lot? Really fast? Not really. It looks like they're kind of going down the same amount, pretty close to it. A little bit. Are they going down and back up? No, so it's probably a linear one, but I don't know. So we're going to L2 and put in 170, 161.5, 153, and 144.5. Remember, don't forget to hit enter. Now I can graph this one, but what am I going to have to fix before I graph it? My window. If I'm on a standard window, negative 10 to 10, are those points? Whoops, I didn't. Take out y equals. Well, first of all, do I have anything in there? No, but going back to that table, my x's have got to show me between 20 and 50. My y's have got to show me between 144 and 170, right? So I'm going to have to change my window irregardless. But let's calculate the regression. So we guessed the linear. So stat, calculate 4. Now notice, here's where I said, it's going to come up L1 and L2. So if you delete one of those, you're up a creek. So L1 and L2. Now, we want to store the regression equations. Everybody remember how to do this one? Alpha, trace, and we're picking Y1, that's where we want it, Y1. And that tells the calculator, hey, whatever you get, put it in the calculator so we can graph it. And then hit calculate. Alright, now, anybody get that? Did anybody get more than that? Nobody got more than that. We're in trouble then. There's one thing we're looking for. I'm so hoping somebody would remember. What variable tells us if it's a good fit or not? Do what? No, not A. It's not one up there. That's why we're in trouble, because it's not listed up there. Which means we got to do this under our calculator. Nope. Alright, we're going to have to turn it on because this calculator's been reset. And if nobody's just showing up with something else, then we're going to turn everybody's on. We have to turn on the diagnostic. Go to mode. Where it says diagnostic, we want it to be on. There's another way to do it, but this is the easiest one. So you have to go over to where on is flashing, and then you have to hit enter for it to take effect. So you have to turn your diagnostics on. And I'm telling you, I will remind you before you take, well, not the day you take your test, but the day before to do this. You've got to turn the diagnostics back on. Because when your calculator will be taken up before you take your test. The day before, I'll take them all up just to make sure everybody has a calculator. But once that happens, I have to reset them. So you're going to have to remember this. So if we quit out of this and do our regression again, so stat count 4, maybe we got to store it again. So alpha trace 1. Now, did it give me more stuff? What variable tells us this is a good fit? What place? R. Anybody remember what R stands for? Do what? No. It does start with an R. I don't know how I use R, but it does start with an R. Anybody remember? This is called the correlation coefficient. Oh, we spent much time on this. Correlation coefficient. Very, very important that you know where that is. Correlation coefficient. You did not have that written down. Write it down, please. That correlation coefficient. We spent a lot of time on this. On that correlation coefficient, it can go from -1 all the way to 1, positive 1. So this is a perfect negative correlation. I don't know if I'm spelling that right. Anyway, 0's right in the middle. What would 0 be? -1 is a perfect negative correlation. What is 0? What does 0 mean? Nothing. So would they be correlated at all if they had a 0? No, so this is no correlation whatsoever. I don't know if there's 2 O's or 2 R's. I have no idea. That's why I do math. I think it's 2 R's, but I don't know. So positive 1 is going to be a perfect positive correlation. If you want to know this, very, very important. You will probably have 2 questions on that. So they're going to say, hey, the correlation is -0.9. And they're going to give you 4 descriptions. Does this mean that these 2 variables are correlated or not? Like I just said, -0.9. Let me see. So my 2 variables are the more time I spend playing video games, what happens to my grades? So as the more time I spend playing video games, what happens to my grades? They go down. So if one goes up, the other goes down. That's a negative correlation. The more time I spend studying, what happens to my grades? They go up. Perfect positive correlation. So if they gave you something that said, this is just an example, like they're going to say R equals 0.98. They may not even say R. They may just say the correlation coefficient is 0.98. Because in their minds, if they give you R, they're giving you a 10. So they probably won't even put R. They'll just say correlation coefficient. They're going to say, okay, the correlation coefficient between amount of time playing games. Playing games, and okay, that's the X, and your Y is your grade. So let's say, wait a minute, negative. Let's put that negative on there. So the correlation coefficient between amount of time playing games and a person's grade is negative 0.98. What does this mean? And then you'll get answers like, as the, I'm going to start abbreviating, as the amount of time, I need increases. Okay, so I'm not going to write this all out. As the amount of time increases, the grade increases. And same thing, as the amount of time increases, the grade decreases. As the amount of time decreases, the grade decreases. Something like that. Or they may say there is no correlation. And what they're expecting you to know is, well, first of all, if it's negative, if one goes up, the other goes down. And then they're going to expect you to put those variables in there. Or another way they could say this, that's one way. Another way, anyway. All right, another way they could say is a strong negative correlation, a weak negative correlation. You could probably guess what I'm about to say. A strong positive correlation or a weak positive correlation. Two ways you're going to see that problem presented. A very easy question here. Why do you think I'm spending all this time? Not necessarily on today, but when I go through it, I say, they're going to give you 2 or 3 of these questions. They're very simple. Why would I do that? Why would I spend time reviewing it all? To help you. For some of you, this test is your only hope in passing. Okay? Your only hope in passing. I'm trying to give you the tools to pass. And it might come down to one question like this, where you're between a 2 and a 3. It may come down to something like that. It may come down to you want to keep an 8. It may come down to you making a 4 or a 5. Something simple like this. And you're going to be so happy when you see these questions. You're like, oh, that's an easy one. I know that. Boom, I'm done. All right, so now, going back to what we were doing before. We ran this regression. We did a linear regression, and that's the best I can get, -1. So is that a good one? It's a perfect one, right? Okay, now, let's do that same thing. Let's keep those numbers in there, and let's do the quadratic regression. I don't really care about storing it. I just want to go in here and look at the R. You see an R there? I don't see an R there. I see the exponential. I thought I hit it. Almost pretty close to it, doesn't it? But did it give me an R? It gave me an R pretty close to it, but most of those, we're trying to pick the one that's as close to 1 or positive 1 or negative 1 as possible. So if you're doing something like this, here's what I would recommend. Let's fix our windows first before we start graphing these. We know we went from 20 to 50, right? For the x's. So we don't want exactly 20, we don't want exactly 50. We want to go below it and above it. So I'm just going to put 0 to 60, and I'm going to count by 10. Everybody okay with that? I can count by 5. Doesn't matter. I count by, whoops, wrong one. 0 to 60, count by 5. You don't want it to be too spread out. We'll put 5 there. Y minimum, the lowest one they had was 144. and the highest one was 170. So I'm just gonna put 0 to, I'm gonna put 100 to 200. And I'm gonna count by 5 again. Hello? I wish. No, actually, I'm good. Thank you, though. Maybe a drink, that'd be about it. Okay, thank you. Bye-bye. Everybody got those? All right, now, let's go back through that. That was the one that we put in there when we sorted to Y1. So let's do the quadratic one. So go stat, calc, quadratic. But down here on store regression, we don't want to put it in Y1. We want to put it in, what's the next one after Y1? Y2. So we're going to go alpha, trace, but then I'm going to hit Y2 this time and calculate. So I just wanted to put that equation in there. So it's just writing that equation in there for us. Now I'm going to do the same thing, but except I'm going to do the exponential. Stat, calculate the exponential, but this time I'm going to store that one in Y3. So I'm going to go alpha, trace, Y3, and calculate. So it should put every one of those in there for us. So if I go to my Y equals, all three of them are in there. I didn't have to type them in there myself. Now, I want to see these individual points. So I want to turn my stat plot on. So I'm going to go to second stat plot, and number 1, you know, this is off. So I'm going to go to number 1. I'm going to hit enter, so on is the one flashing, not off. And then I'm going to graph it. Let's see what I get. So there's my point. There's the line. There's the red one. And there's the black one. They all kind of look the same, don't they? Are we getting the whole picture though? What would you guess right now? Linear, quadratic, or exponential? How many would say linear? How many would say quadratic? How many would say exponential? Okay, so when we did the linear, we got a perfect negative one, right? When we did the quadratic, did it give us an R? It didn't, did it? So it's not a quadratic. It didn't give us an R. It gave us an R squared, but we're not going to get to that. On the exponential, what did it give us? Negative 0.99. But the calculator's only doing it based on those 4 points, and they all 4 hit those points, don't they? But we know that a quadratic looks like a U. We know an exponential doesn't gradually go down, does it? It goes down really steep. You don't necessarily have to look at the graph. It just gives you an idea. But go with your gut. It is a linear. How could I have looked at that based on that table? Let's say I'm still questioning myself. If I go to that table, that table we just put in, 20, 30, 40, 50, and then we had 170, 161.5, 153, and 144.5. How would I know based on the table? Are these X's, do they have a common difference here? Their common difference is 10, right? What's 161.5 minus 170? I calculated. I think it's right. Okay, say 153 minus 161.5. Negative 8.5? 144.5 minus 153. You want to take a guess what it is? Negative 8.5. That's a first difference, so we know it is a linear. Okay? Now, what they're going to ask you for is the equation, which, good Lord, the calculator does for us. We just did all 3 of them, didn't we? Which one's the linear equation? Out there. So it gave us the linear equation, so that's the one we would choose. Alright, so go down to number 2. Number 2. Volleyball hot. the height of the volleyball once you hit it? Technically, you want the volleyball height to go down, don't you? What do you think? Just looking at that table, what do you think it is? Looking at those Y values. It starts at 10 and goes to 12.7 and then goes back down to 12 and back down to 9. Lady, you got an extra question? Ready to guess? What do y'all think that does? What do you think, Debbie? A quadratic. Why would you say quadratic? Because it starts low, goes up, and then goes back down, right? So it's probably a quadratic. So let's put those in there. Let's see. So go to y equals, clear everything out. Go back to stat and edit. Clear your tables. Don't delete. Clear and enter. Alright, so let's put these in here. So 0.4, 0.8, 1, and 1.2. One thing I'm thinking right here, based on what I just graphed, what should that tell me? What am I thinking? What am I going to have to do? Do what? I gotta change that window. I don't know if somebody said that, but we remember we were doing 20, 30, 40, and 50, so we're definitely going to change that window. Alright, so let's go back to L2. So 10.44, 12.76, 12, and 9.96. Ah, geez. 9.96. There we go. Before I do anything, I'm going to go zoom 6 just to put me on that standard window. Do I see anything there? Yeah, one little dot up at the top, so I still got my stat plot on, but I don't need any of these negatives, x's or negative y's, do I? Because none of those were negative. What do I need to go, do I need to stretch this out on my x's? I'm going from 0.4 to 1.2. Do I need to see negative 10 to 10? No, all I need to see is from 0 to 2. So I'm going to change that one to a 0, that one to a 2, but now I don't want to count my ones. I need to spread that graph out. Not 5, because we're only going from 0 to 2. 0.5 maybe? 0.2 maybe? Wouldn't matter. If I did 0.5, we can do that, it doesn't matter. Y scale, we're going from, let's see, 9.9 to 12.7. So what do you think on that one? Do what? 8 to 13? Okay, so we'll just do 8 to 13. What do you want to count by? Ones again? I mean, it doesn't matter. We got ones in there. So if I hit graph, can I see more of my points? Yeah. Now just looking at this graph, does it look like a straight line would hit all of them? No. Does it look like an exponential where it starts small and then goes up? Maybe starts big and goes down. That'd be a stretch though. Does it look like a quadratic where it goes up and comes back down? Yeah. Does that make sense on a volleyball? Kelsey, you're a setter. You set the ball at the eye level, right? It goes up, and then it's coming back down as the hitter hits it, and then it definitely goes down. So probably a quadratic would be a good guess. So if they're asking us for that equation, we're going to go to stat, count, and based on our guess, which one do we think? Quadratic, so 5. I'm going to put it in, doesn't matter, I've only got 1 in there, so I'm just going to go to Y1, so alpha trace 1. And calculate, and there we go. So let's hit, so our equation, it's in there, negative 16x squared plus 25x plus 3, so the calculator gave us our equation. Let's graph and see how well that hits it. It's pretty good, doesn't it? Is that a, who can define or describe that correlation? Describe that correlation for me. Describe about that correlation? You could have seen it, you think might be, when you first got decided they're positive or negative, you have to be paying attention to what I was saying first. But if it's positive or negative, the window's probably one. Okay, so what kind of correlation is this? How well did those points in that graph line up? Pretty good, don't they? What did it give us on our, well, on our regression? What did it give us on that regression? There's a 1, didn't it? So it stayed perfect. Why does it not say a positive or a negative? Why would it not be a positive or a negative correlation on the quadratic? A correlation, look back at my description, think about this. As a negative correlation, as one goes up, the other goes down, right? Well, what happens on a quadratic? Like on a line, as one goes up, the other goes up, or as one goes down, the other goes down. On an exponential, as one goes up, the other one goes up. As one goes down, the other one goes up. What happens on a quadratic, though? Switching direction, didn't it? So, on here, have you ever seen an arc? I'm not going to see that on here. But even if we were still confused about it, what could we look at? We could look at this table and decide what's going on. So what are those differing by? 0.8 minus 0.4 is what? Okay, I can stand up here all day long, but if you're not willing to pay attention, you might as well put your head down and just say, I'm done. I'm not even going to try to pass it. Like I said, there's about 10 of you right now. This is your only hope. Your only hope of passing. If I were you, I'd definitely be trying to pay attention. If I did nothing for the last 60 days, I'd be busting my hump for the next 30. Unless you simply want to take the class over, and that's your choice. But if you keep doing the same thing that you've been doing, you're going to get the same result. Look up insanity. Same actions are going to get you the same result. So, crap in will give you crap out. Some of you are doing that. What are my differences on my x's? I subtracted 0.8 minus 0.4, 1 minus 0.8, 1.2 minus 1. This one's 0.4, right? This one's 0.2. What's this one? 0.2. So can I look at those differences? If these aren't the same, are these going to be the same? No, you can't use the table. So you have to know how to do this regression while we're doing this. Alright, now, on the other side, you have 4 problems. You have 4 problems on the other side. Each one of them has a place for you to put a graph. So you're going to have to do your window on your graph. Each one of them say, does the data represent a linear, quadratic, or exponential? And the equation. You got 4 problems that we'll do tomorrow. You probably get it done right now, actually. You want to do it on another sheet? Actually, you need to do it on another sheet and turn it in. You can't turn this in. You need to do it on another sheet of paper and turn it in.